All right, 9.3, similar right triangles. Here we're going to be talking about, as you can tell, similar right triangles, and they're all going to be kind of nested in each other. You can see that in the picture on the right. Starting off the right triangle similarity theorem, if the altitude, and I'll define altitude, if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original and to each other. An altitude is this piece inside a triangle. It comes altitude. We'll say that it meets a side at a right angle and the opposite vertex. I'm sure there's a better definition, but that is what it is. It touches the side down here at its right angle, and it also touches the opposite vertex. In this case, it's C. So that altitude there, that's CD, separates the big triangle ABC into two smaller triangles, ACD and CBD. Let's look at number 10. We're going to identify all the similar triangles. So I'm going to draw all three triangles separately. Actually, I'm going to leave the big one there, and I'm going to make the other ones kind of drawn in the same orientation. So we're going to have a smaller triangle there, and then a medium triangle there. Dealing with the one on the left, these are going to be our right angles. They're kind of in the air. We have point Y for both of them are in the air. Now looking at the left triangle, the short side there goes across to W, and the other one is X. Now for the triangle that is on the right, we have the right angle already up in the air. Across from the long side is V, and then across from the short side is X. So those aren't super beautiful pictures, but those are the three triangles that are in the larger triangle. Example 11, we want to find the value of H. H is the altitude, right? Right here. So we're talking about similar triangles. This is going to be just an easy similar triangles rule or problem. I'm going to need to separate this into some different triangles. I'm going to take this left triangle and draw it here. So that'll be, here's my right angle. D is at my right angle. And then we'll have B and A. Well, AB is 12. DA, we don't know what DA is. We know what DB is, though. DB is H. And yeah, that's all we need. We have H in 16, 12, and 20. So H over 16 equals 12 over 20. Solving that, we should get, let me type that in the calculator, 12 times 16 equals divided by 20, 9.6. There we are. Next up, a geometric mean, right? Mean means average, correct? So this is a different way to find an average. It's a different type of average. The geometric mean of two positive numbers, a, b, is the positive number x that satisfies this proportion there. A over x equals x over b. If we were to cross multiply right here, we'd have x squared and ab, which is written right here. And then we can take our root and say, well, x equals the square root of ab. So if you're told to find the geometric mean of two numbers, you're going to plug it into that right there. All right, next up we have this. I'm going to skip this because there's a problem later on that does pretty well the same thing. Number 12. Oh, I just said that if we have this geometric mean, we're going to say, well, we've got x equals the square root of AB. So I'm just going to plug in 18 and 45. X equals square root 18 times 45. Well, what is the square root of 18 times 45? Oops, that's 14. 45. That looks like 28.46. And I'm okay with us just finding a decimal there for now. If we wanted to find the precise answer there, we would say, well, this is the same thing as the square root of 810, and we can split that up. 10 and 81. I know 81 turns into a 9, so this is the same thing as 9 root 10, and 10 will not split up. So there's the precise answer. Maybe that's the better answer. All right, next up, 9.7, the geometric mean altitude theorem. In a right triangle, the altitude to the hypotenuse divides the hypotenuse into two segments, right? That's talking about this segment and this segment. The lengths of the altitude, the length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. So the altitude here, that's CD, is equal to AD and DB. Or excuse me, the altitude squared is equal to AD times BD. We're going to need to use that, right? Had we known that theorem, we would have been able to do this problem. Actually, we wouldn't have been able to do that problem faster because we had this 20 there. But later on, we'll be able to do some problems faster. 9.8, geometric mean leg theorem. In a right triangle, the altitude to the hypotenuse divides the hypotenuse into two segments, right? We already know that. The length of each leg of the right triangle, is talking about this leg, or here, let me do a different color. This leg or this leg is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So if we're talking about the left side, the purple side, that is AC. So AC is the geometric mean of AD times AB, the whole thing. All right. So if we're looking at the large right triangle with the altitude drawn in it, the left or the right leg, you can pick which one you want to do. In this case, we talked about the left leg. The left leg, the purple leg, AC, is the geometric mean. So we could say AC squared equals the shorter piece of the hypotenuse times the whole thing. All right, let's look at example 13. This one, we're going to use that theorem right there. We know that x squared is like the left leg. It's going to be equal to the piece of the hypotenuse that's next to it times the whole thing, which is going to be 11. So x squared is 55, and x equals the square root of 55. Root 55 won't split up, but I'm going to write it as a decimal. It would be 7.42. So there would be our answer. On the homework, I'd still like you to leave it in simplest radical form. That would be the top one. Number 14, we're supposed to identify the similar triangles. So let's see if we can do this without drawing them all separately. We start off and we have the big triangle, we'll say K, and we'll go across its short leg, L, and then J, is going to be similar to triangle. And let's look at the triangle that's on the left here. Its right angle is M, and then across its, where do we go? We went across the short piece first, M, K, J. And then lastly, we have the right triangle, or the triangle that is on the right. its right angle is M, across its shorter leg is L, and then K.
Skip this next problem and move on to the
All
next
right, looking
page.
at these problems here. In the left piece, we're going to start off with X, and then we're going to look up here just a little bit. We have this similarity statement here, so I'm going to kind of use it. X is Km in this triangle, so Km, I'm going to look at where it is. Km would be here, or, well, we'll just use that one. Km, it's in the first two spots, so now I'm going to go to the first triangle and look at the first two spots as KL, which is the right side of the big triangle, so 21. And then I just need to pick another side. We'll say KJ and then LJ. Well, KJ is the left piece, so that's going to be 20, over LJ, which is this bottom piece, so that's 29. Whenever I type this in my calculator, I get X equals 420 over 29, and we will leave it as a fraction there. Next up, another problem. This one's set up in a very similar way. Let's see if we can kind of find a way to generalize these. We've got X over, well, on the left piece we went to 21. That was the right side. And in the left piece we went to the 20 over 29. So in this case it's going to be 15 over 17. All right, that's kind of the faster way of doing this rather than having to draw all three separately and writing all the similarities statements. So here I say, well, 15 times 8, that gives me 120, so I'll say X equals 120, and I'll check and see if 17 divides it. It does not, so we will just leave it as there. All right, next up, this one here, we can use a theorem. Let's see which theorem it was called. This is going to be the Leg Theorem. So we're going to say that the leg of the triangle, we're talking about like the red piece there, is going to be equal to, squared is going to be equal to the little piece of the hypotenuse times the big hypotenuse. So x squared is going to be equal to 8 times, that whole thing is 40 times 40. So x squared equals, what is 8 times 40? 8 times 40 is 320. So x is root 320. We need to break it apart. 320 I know breaks into 8 and 40. 8 is 2, 2, and 2. I have a pair of 2's there. 40 would be 4 and 10. 4, 2 and 2 there. 2 and 5. So we have a pair of 2's right here. A pair of 2's here. And then a single 5. So we have 3 pairs of 2's. So that's going to be 2 times 2 times 2. And then left underneath our root is a 5. 2, 2, and 2 gives me 8, root 5. And that's that one. Next up, this one's written a little bit differently. It's kind of in a different orientation. Here's our leg. So we're going to approach it in the same way that we did the last problem, except our variable is going to be in a different spot. So we know that the leg squared, 6 squared, is equal to the small piece of the hypotenuse, x, times the whole thing, which in this case is 12. So here I can solve for x, and well, 6 squared is 36, divided by 12 gives me 3. That one's nice and easy. All right, next up, find the geometric mean of these two numbers, 3 and 12. So we'll say, well, x squared equals 3 times 12. So x equals, I'm going to go ahead and put the root in there, 3 times 12. Now I need to look at 3 times 12 and find its pairs. Well, 12 will split up into, actually, 3 times 12 is 36, isn't it? So x is going to be 6. We don't even have to worry about splitting it up. Same thing for this next problem. We'll say, well, x squared is 10 times 24. So x equals the square root of 10 times 24. Now I want to try to split these apart. 10 times 24, well, 10 would split up into 5 and 2. 24 would split up into 12 and 2, 6 and 2, 3 and 2. So we have a pair of 2's right here, a pair of 2's here, a single 5, and a single 6. So x is 4 root 6. And there we are. And we're done. Cool. I'm going to say that I think the hardest problems are going to be the ones that look a little bit more like these, or like these two right here. So it would be make sure that you have those written in your notes somewhere. All right. Good luck on the homework.